So logical propositions are one thing, and they can feel pretty simple to work with when they're coming at us sort of one and two at a time. But a lot of the time in analysis, we work with propositions which are not single propositions, but are entire families full of propositions that are quantified on the real numbers, or quantified on the integers, or quantified on the natural numbers. In other words, not just a single proposition, but one proposition for every natural number, or one proposition for every real number. And those sets are so gigantic, we couldn't possibly hope to prove each of the cases one at a time, because there's infinitely many cases to prove. So we form what are called quantified propositions. And quantified propositions come in these two different flavors: a universally quantified statement and an existentially quantified statement. The way it works is we can work with a family of propositions. I call it P, call it a function from a set S into the Boolean set of true and false. Here the set S is often something like the natural numbers or the real numbers or the rational numbers or something like that. So some really, really large set. And so we say that a logical statement has been universally quantified if that statement is said to be true on the entire set S. So in other words, every single element of the set here, S, that I pick, it lands on true when we apply this function to it. And so we call that a universally quantified statement. And usually in words, it looks like for all x belonging to S, we have the statement P of x is true. Right? Very often we'll use notation for all when we're being shorthandy. You know, like if I'm sort of scribbling something on a napkin or something, I might use the upside down A to mean for all. But probably when you're writing your proofs in your analysis course, you want to write them out in the English. So try to avoid using these little shorthand notations when you're presenting a final product, a finished, polished proof. But along the way, feel free to use them for your own sake, just to save yourself a little bit of writing. And so a universally quantified statement for all x in S, we have P of x is true. That's true only when it's true for every x that I could choose from the set S. And so it's equivalent to the if-then statement. If x belongs to S, then P of x is true. And so that should be true for every x that belongs to S that we could possibly pick. So that's one side of the coin, the universal quantified statements. The other side are what are called the existential quantifiers. Rather than needing to be true for every single element of S, an existential statement is the claim that it's true for at least one element of the set S. So we know that it's not false everywhere. It's true at least for one, and perhaps more, but at least one element of the set S. So it's true on at least some of the set of quantification. And so in words, we usually use words like there exists. There exists an element x in the set S such that P of x is true. So we call it existential quantifier. There exists is usually in shorthand written as a backwards E. Right? But again, when you actually write a polished proof, you probably want to use the words rather than the symbols. And so logically speaking, the content of an existentially quantified statement is that x belongs to S and P of x is true. Right? So it doesn't have to be true for every x that I pick, but there should exist at least one element x that I pick such that x belongs to S is true and also P of x is true. So that's why we have a conjunction here. There needs to be at least one example where both of those statements are true statements, compared to the universal, where the statement P of x has to be true for any possible choice of x belonging to my set of quantification. So one of the reasons that quantified statements are tricky to work with is the burden of proof that they set up in order to prove that a quantified statement is true. If I want to show that, for example, all prime numbers are odd, right? There's an example of a secret universal quantifier. Let's say for all prime numbers x, we have the proposition that that prime number is odd. Right? If I want to prove that statement is true, I have to show that it's true for every single prime number of which there are infinitely many. Right? But if I want to show that that statement is false, my burden of proof is a lot lower. It's a lot easier to show that a universal statement fails, because a universal statement fails when any one possible example that we could choose fails. Any circumstance, if I turn this statement around here, right, if I negate this if-then statement, if I want to prove that my universal is false, I negate this if-then statement. And the negation of an if-then statement is the statement that the premise may be true, but the conclusion may be false. And so in order to prove that it's not true that all prime numbers are odd, I would just have to find a prime number So an x which belongs to my set of prime numbers, which is not odd, and have both of those statements be found to be true. And the obvious example, in fact the only example, is the number 2. Right? 2 is prime, and 2 is not odd. Therefore, we've shown that this universal statement is false. So one bad apple spoils the entire bunch when you're trying to prove that a universal statement is true. So a universal statement is false only in the case when it fails for even one example. We often call those counterexamples in mathematics, right? You find me one counterexample to a universal statement, and that universal statement is categorically false. So, of course, the existential statements have a higher burden to disprove and a lower burden to prove. If you're asked to prove that there exists an even prime number, you can do that by being very specific and giving me one example. Right? 2 is even and it's prime, therefore it's true that there exists an even prime number. Right? So to prove that an existential statement is true, the burden of proof is very low. You can either be constructive, supply a specific example, and be done. Or you can also prove existential statements in a non-constructive way. You can read more about that in our workbook if you want to. And so to prove that an existential statement is false, the burden is much higher. Because in order for an existential statement to be falsified, let's negate this form of it, right? We would need to show that either x doesn't belong to S, so sort of write that way, or not p of x. So to prove that an existential statement is false, we need to either show, well, what we need to show is that it's not possible for p of x to be true for any element x that belongs to S, right? And so an existential statement is only false when it fails for every possible example. So if I claim there exists an even prime number, and you think I'm wrong, you have to show me that every prime number is not even. Right? And so when we negate an existential statement, it becomes a universal statement. When we negate a universal statement, it becomes an existential statement. So if I have to prove something for all, and I turn that around and make it the negation, then that negation becomes that there exists. Similarly, if I have to prove something exists, and I think that maybe negating that statement will help me in my proof, negating that statement turns it into a universal instead. So what it does is it gives you a lot of flexibility as a discoverer and an author of proof. If you don't like the hand that you're dealt, if you don't like trying to deal with a universal statement, trying to prove that it's true, for example, then maybe working with its negation, such as in a proof by contradiction, can be a little bit easier because it turns universal into existential instead, and vice versa. If you're having a hard time with an existential statement being true, you might be able to use its negation as a false statement, which is a universal. Right? So you get to, as the author of a proof, the architect of a proof, go back and forth between those two worlds by using the negation. So the task I want to set you to is to stare into the void for a moment at a very challenging assertion. It's actually part of a definition that you'll see in the second semester of real analysis, if you get there. It's a definition of what's called a uniformly continuous function on the real numbers. And I want to reassure you by saying that the definitions that you work with in real analysis mostly will not be this complex. If your heart just stopped looking at this, my heart stopped having to write that. But it's a nasty definition. So to read it out in words, this is the definition of a function being uniformly continuous on all of the real numbers. It says, for all values of the Greek letter epsilon, for all epsilons that are positive, and for all real numbers x, we can find there exists a delta, which is positive, such that for all real numbers y that we choose, it's true that if the absolute value of the difference of x and y is less than delta, then the absolute value of the difference between f of x and f of y is less than epsilon. So there's a lot of pieces involved in this definition. And so one of the things that you might do in the second semester of real analysis is somebody might hand you a function, f of x equals x squared, right? And say, prove to me that this function satisfies this definition of uniform continuity. Right? And so you would need to verify that this is a true statement for the function that you were handed. What I want for us to do now is not to worry about the particulars of how we might use this in a proof or in verifying an example, but just to think about what it would look like to negate this statement. What would a function which is not uniformly continuous by this definition, what would a function that doesn't do this satisfied? What definition, what string of quantifiers? So let's use the information that's on this slide, 5 or so minutes in the breakout rooms, try and figure out how to turn this statement on its head.